Hello, everyone. In the last video, we talked about the governing equations of incompressible flow. Today, we are going to explore further and derive the dimensionless form of governing equations and the origins of finite element method. We put the dimensional form of governing equations on top of this page, which we derived in the last video. We also assumed that you had learned the non-dimensionalization techniques in the fluid mechanics class. Now, we can use the following dimensionless groups to non-dimensionalize the velocity and pressure terms in the continuity equation and Navier-Stokes equation. A very obvious change is that we replace the kinematic viscosity with the reciprocal of Reynolds number. It implies that the diffusion term is vanishing as Reynolds number keeps increasing. In other words, from the bifurcation theory, Reynolds number acts as a bifurcation parameter which has the capability to change the nature of partial differential equation characteristics. It is equivalent to say that the advection term becomes more and more dominant in turbulent flow. However, this change of system nature is nor uniform over the entire domain. Some places is more diffusion dominant, and some places are more advection dominant. Therefore, the turbulent flow is chaotic and irregular from places to places. Nonetheless, we put aside the discussion of turbulent flow in future videos and continue our discussion of Petrov-Galerkin method. Now, after all these steps, we obtain the dimensionless forms of governing equations, as shown at the bottom of this page. Before working on the Petrov-Galerkin finite element formulation, it is a good time to briefly cover the mathematical background and historical origins of the finite element methods. Finite element method is deeply rooted in the advancement and development of the applied mathematics over centuries. In the early 1940s to 1950s, the formal derivation of FEM as we know it began in structural mechanics, particularly for analyzing complex aircraft frames and wings. Engineers like Richard Courant used piecewise polynomial functions to approximate solutions of variational problems. This is frequently cited as the first finite element type formulation. In the 1950s to 1960s, Turner, Clough, Martin, and Top published the seminal paper Stiffness and Deflection of Complex Structures, where the phrase finite element method was popularized. In 1960s, Ray Clough introduced the term finite element explicitly. At this point, finite element method became a practical numerical tool in structural analysis. It is in 1970s, mathematicians and engineers extended finite element method from elasticity to fluid mechanics, heat transfer, electromagnetism, and beyond. This was the moment the variational or weak form and Galerkin interpretations were formalized. While reading finite element books, you may find that there are different origins of finite element methods in the history. In fact, they are all true, since the multiple origins come from the fact that different fields rediscovered similar ideas independently. From the mathematical perspective, finite element method is usually seen as a generalization of the Ritz method and Galerkin method, which themselves came from functional analysis. Mathematicians see finite element as a systematic way to approximate partial differential equation solutions in function spaces. However, this agreement was reached over a long period of time along with the advancement of applied mathematics. Finite element methods were first developed for structural analysis, in which people are more interested in the displacement of material subjected to external forces. Therefore, researchers usually explain these methods from the viewpoints of strain energy, total energy, internal energy, work done, and so on. The solution, which is the admissible path of deflection of the structure, is solved by minimizing the potential energy, balance the virtual work and internal energy, and so on. This is what we called variational approach or energy principle-based methods. Later on, when we looked at the other problems, especially the non-conservative systems, for instance Navier-Stokes equation, a more general interpretation of finite element methods is based on the weighted residuals perspective, in which what are trying to do is to minimize the residual or numerical error globally, instead of enforcing absolute zero error at each point in the domain. For those who realize that the finite element projection is indeed taking a quadratic form, he or she will be more comfortable to explain the finite element method from a projection and optimization viewpoint. Thinking FEM is in fact a quadratic optimization problem. On the other hand, finite element theory can also be interpreted from the functional analysis perspective, in which the applications of test and trial functions can be understood as lower-dimensional projection of the infinite-dimensional solution space that in my opinion, I am more comfortable to understand finite element methods as an optimization problem, in which we are minimizing the residual or numerical error globally in a weak sense. It means that we are not trying to make absolute zero numerical error, but control it to its minimal over the entire computational domain using a specific test and trial functions to form a quadratic form, and look for this unique numerical solution as a projection of the solution space on a plane consisting of the chosen test function as the subspace of the solution space. This projection will give the best fit of the numerical solution to the analytical solution space, subjected to your chosen finite lower-dimensional test function space. Now, let us look into more details of variational principle. In variational principle, our focus is on the energy related to structural deformation. We talk about structure here because it is the major background from which variational principle-based finite element formulations were derived. Hamilton's principle is a very general form for time-domain variational principle on conservative system, for instance, the material deformation problems. Hamilton's principle focuses on action stationarity, which says the actual path of a conservative mechanical system takes between two time instants makes the action integral stationary, usually the minimum. You may also heard about principle of virtual work. In fact, it is basically the static equilibrium form of Hamilton's principle for statics of linear or nonlinear elasticity problems. This principle is formed by balancing the forces. Furthermore, another equivalent finite element formulation for static structural analysis is called principle minimum potential energy. It says that the deflection path of the structure takes the path which possesses the minimum potential energy. This method works well for static linear elasticity problems. Finally, Rayleigh-Ritz method is basically an approximation approach to solve these finite element formulations, in which the displacement is assumed as a linear combination of trial functions satisfying boundary conditions to minimize the total potential energy in structure. The variational method works well for conservative structural deformation problems. However, we all know that the finite element method can be applied to non-conservative systems, for instance, the Navier-Stokes equation. Therefore, a more general approach is adopted to extend the applications of finite element methods. This is the weighted residual method. The fundamental idea is that we project the residual of the PDE, which is computed by using the left-hand side of the PDE minus the right-hand side of the PDE, onto a finite lower-dimensional function space, what we call the test function, such that globally this residual is minimized in the computational domain in the weak sense. Here, the global minimization is achieved by setting the integration of the product of the test function and the residual over the entire domain as zero. The weak sense refers to lowering the requirement of the solution space. For instance, lowering its order of differentiation and smoothness of the solution space, which is done by the integration by parts operation based on Stokes' theorem and allowing discontinuity along the edges of elements. Because of the robustness and generality of this approach, it is usually considered the standard procedure in finite element methods nowadays. The famous Galerkin method, Petrov-Galerkin method, and least squares method all belong to this category. Now, after our discussion on the variational principle approach and weighted residual approach, if you also look into some reference books on the finite element method, you should realize that both variational principle and weighted residual methods result in a quadratic form of a linear system of finite element formulation as shown below, in which we approximate the solution by a trial function, or what we call its shape function, and the corresponding nodal unknowns. If we plug them into the energy functional, it leads to a discrete energy equation, which we called it pi. In finite element theory, we basically aim at minimizing the potential energy. In order to do so, we will differentiate this potential energy and find where its first-order derivative is zero. This corresponds to its minimum potential energy. Then we arrive at our familiar finite element linear algebraic system. Therefore, the finite element algebraic problem is precisely the first-order optimality condition of a quadratic optimization problem. If we consider that there is a functional space in which the analytical solution of a PDE lies, we call this functional space as solution space. It is a smooth and infinite-dimensional space. Basically, in functional analysis, we study this function as an operator, which is usually differentiation or integration to project another function, for instance, the solution space. Functional analysis is linked to finite element formulations in the sense that finite element theory provides a way to project this smooth, infinite-dimensional solution space onto a finite lower-dimensional solution space in which the numerical solution lies. Therefore, the finite-dimensional numerical solution space is considered as the best fit of the original smooth, infinite-dimensional solution space based on your chosen test function space. In other words, your numerical solution is the low-dimensional projection of the analytical solution onto your chosen test function space. Now, continue our previous discussion on functional analysis. We can formally introduce some important spaces in finite element theory. The first one is Hilbert space. It is the inner product space to define variational formulations, in which we seek a solution among all possible solutions in this Hilbert space and consider all functions in Hilbert space are square integrable. Hilbert space, in fact, is the subspace of Banach space, a complete normed vector space. Whereas the Sobolev space, consisting of the admissible solution of PDEs in the Hilbert space, is a subset of Hilbert space and also the true solution space of finite element weak form. In Sobolev space, it says that the derivatives of functions, up to order k, are square integrable. On the other hand, the finite element subspace refers to the finite lower-dimensional piecewise polynomial functions, which is a subspace of Sobolev space. This is the function space where our discrete numerical solution lay in. Its dimensional is also dependent on your spatial discretization in mesh. Furthermore, specifically, the test function refers to the function space where the residual of PDE is projected onto. It determines how the residual of PDE is spatially projected over the entire computational domain and minimized, whereas the trial function is the so-called finite element subspace, which the finite low-dimensional numerical solution lay in. This is exactly the finite low-dimensional function space, where we project our smooth infinite-dimensional solution space onto. Now, at this stage, we are fully ready to work on the Petrov-Galerkin finite element formulation for the dimensionless, incompressible Navier-Stokes equation. We will start working on it in the next video.